So these are the results when we do not invest in our system, and we can check how things went. And we check every single process of our system. Okay, we have this pivot table, and we have elements of information for the cleaner, for the coat of the conveyor. There are some general elements of information, grinders, hardener, and so on. For example, we have the cleaner, which remember had an input buffer, and we can learn from the model what is the average amount of items we have prior to the cleaner, which is 0.2361. At the end of the simulation, there's no items waiting to be cleaned. The maximum value that was achieved was 7, and the minimum is 0, of course, because that is something natural. And as to the processing, the space we have for cleaning, for actually cleaning our valves, on average, we had this 0.5516. Even at the end of the simulation, there was only 1. At maximum, we had 1, and minimum 0. Okay, so this gives us an idea. If we had something very close to 1, that would mean that we are having that cleaner pretty much working all the time, or working or blocked, which is not the case because the cleaning stage is the last one of our system. But we have extra information about the utilization rates, so we can see for how long or which percentage of the time the cleaner has been blocked. Blocked means that it's finished doing whatever the process is supposed to do, and there's no room for the entities, for the parts to move on. So until the next stage, the next process finishes, in this case it will be the cleaner, has to be blocked. That is not the case for the cleaner because it's, as I said before, the last process of our system. This is the fail time. Almost 8% of the time the cleaner was failed. That meant that it was either broken down or waiting to be repaired. 40% of the time was processing, and 44% was stopped. Stopped means that it was waiting. It was available. So it was in a ready state, and if it had valves to clean, it would have been able to do it. So this is a capacity that is not utilized because the rest of the system upwards, upstream, is not providing any valves for the cleaner to clean. Okay, so that reveals relevant sources of information. So that's something that we should take a look at because this is not working as much as it could. We have the same for the coater, for the conveyor. Okay, we have two elements, two conveyors, conveyor 2 and conveyor 1, and we have different elements of information, but in something for them both when they are working together. We have general information as to how many bars were rejected, because remember that there is a buffer for bars to be received into the system. If the buffer is full, they are rejected. So there's a high rejection rate, as we can see. So that means that whatever is upstream of this plant is working faster than the plant itself, and we have to reject. Of course, we are not going to do that in a real system, so that might mean that we have to stop the plant or the stage upstream, but that is something we should take care of. And we have the hourly production we saw previously in the layout, the investment, which is 0, and the total production we already saw. And we have similar information for the rest of the processes of our system. Okay, so the idea here is that we can identify which is the busiest process of all, and we can try to increase its capacity. And then we'll see the impact and see if the bottleneck is still that process or there's another one which we need to take care of.